So any kind of a discontinuity that you have in the current return path will always cause issues with the speed at which you are able to signal. And that is what we call as the return path discontinuity. Let us say that we take this system and we want to construct a very simple SPICE circuit with it. There are two ways to do that. If you look at the top circuit schematic that is shown, you have a circuit representation that accounts for the interaction between the interconnects in the package and the printed circuit board with the power distribution network, which is shown as VDD and VSS over here, along with the capacitors that you would have on the die. There is also another way of constructing the circuit, which is shown at the bottom. So the question is, which one is the right one to choose? And obviously, the model at the bottom is incorrect, because that model is only valid if you have infinite capacitance between the VDD and the VSS planes of the power distribution network, and we know that that is not the case. Since we do not have this infinite capacitance between the two planes, anytime you switch the circuits, you will create noise, and that noise will show up on the interconnects as part of the signaling environment that is shown over here. Let us now look at current loops when the transistors switch. So let us use the circuit schematic that I showed on the previous slide, which is the correct model to understand the relationship between signal and power integrity. So if you look at the top circuit, what is shown is the current loop in both red as well as the dashed line when you have a low to high transition. And the one at the bottom is when the driver transitions from high to low. So if you look at the two transitions, the path that the current takes is very different. In the case of the low to high transition, you will find that no current flows to the VSS plane. Whereas in the second case, in the case of the high to low transition, there is no current that flows through the VDD planes. So in this example over here, when you switch from low to high, the ground planes will have next to no effect on the signal integrity of the waveform. Similarly, when you have a high to low transition, the VDD plane will have absolutely no effect on the signal integrity of the waveforms because there are no currents flowing through those structures. In reality, we all know that this rarely happens. So let us say that we bring in the on-die capacitance. So as is shown over here, the minute you have the on-die capacitance, the current loop changes quite a bit. So if you now look at the low to high transition, along with the current loop shown on the previous slide, you now have a new current loop. And as a result of that, when you have the low to high transition, both the VDD planes as well as the VSS planes will have a direct effect on the noise that you generate in the system, and therefore they will affect the signal integrity of the waveform. So the case I'm trying to make over here is that unless you can understand the current loops in your system and understand the discontinuities in that current loop, it is absolutely impossible for you to predict the RPDs, the return path discontinuities, and their effect on the signal integrity of the waveform. Let me illustrate this using a simple example, and the example I'm going to choose over here is for a strip line, which is a passive interconnect. So we're not going to look at any of the drivers in the circuit. So if you look at the strip line interconnect, I'm going to look at three scenarios. The first is the strip line interconnect between a voltage between two planes, one at the top and one at the bottom, where the two planes are connected to each other using vias. This is what you would do in an RF kind of an environment because you want to make sure that the two planes are shorted together. The second scenario is when the top plane and the bottom plane are not connected to each other, which is what you would see in a digital system, because the top plane could represent VDD and the bottom plane could represent the VSS supply voltage.